Hello, hello. Am I audible?
Yes, sir.
Yeah. Okay. Okay. Good evening, everyone. I am Nidhi. I'll be taking your problem solving session for this NPTEL course, Graph Theory. So I welcome you to the first problem solving session. So I I'm thinking of waiting for 2-3 minutes to see if other participants join. We'll start like after 2-3 minutes. Okay, hello. Hello everyone. I welcome you to the first problem solving session of the NPTEL course Graph Theory. I hope I am audible to everyone and my screen is visible.
Yes, sir.
Okay. So let's start. So the format of the session is that first we'll recall the concepts that have been covered in the first week. Then we'll be solving some problems related on this related to the same topics, and and you're free to ask in between whatever doubts you have. So feel free to unmute yourself and ask questions if you are not following or something. Okay. So 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 first of all, let's recall the topics that have been covered this week. So the first week was about the introduction to graph. So what is a graph? So a graph is a pair which is given by set of vertices and set of edges. So it is a pair with VE, where V is referring to the set of vertices and E is referring to set of edges. So you can see by edges we mean a subset of v cross v. So if so in this follow so you we can see this is the following graph in which the points are what we calling vertices, and edges are the lines that are joining these vertices. So if a is an edge, that means it is so we have a line joining a and e. So a graph is such a pair. When we know what when uh, giving a graph is equivalent to giving a set of vertices and set of edges. So is there any question? Oh, okay. So now this is one of the example of graph. Now I want to just list out few common examples of graph that you'll encounter everywhere. So first is these complete graph of n vertices. So first of all, when we are given two vertices, we will say that these two vertices are adjacent if we have an edge between them. So in this following graph, in the first graph in which has been drawn this, we can see A and B are adjacent vertices because they have an edge between them, but A, E, they are not adjacent vertices because we don't have an edge between them. So now some some common examples of graph. So so okay, so if you don't have if you don't have any question, then you can mute yourself. If you have question, then unmute yourself. uh, so now for some common examples of graphs you can see. So first are the complete graph on n vertices, which we also denote by kn. by a complete by a complete graph of n vertices, we basically mean that all vertices are adjacent. So if we have any two vertices, there is an edge between them. So these are the complete graphs. Now another common examples of graphs are cycles. So you can cycles are what you will imagine pictorially. So if this is C4, so basically a cycle on four vertices. And then another common examples are trees. So trees are graphs in which we don't have any loops, in which we don't have any don't have any cycles. So now you can see in all these above examples, complete graphs, cycles and trees, we don't have any multiple edges. That is, we don't have any parallel edges. That is, if we have two vertices, there is at most one edge between them. So all the above examples are the examples of simple graphs. But all graphs need not be simple. There are multi graphs also. Now secondly, so once we know what is a graph is, then second concept was the degree of vertex. By degree of vertex, we mean that we want to count all the edges which are adjacent to V. And in the lectures we saw this result, that number of in a graph G, total number of edges equal to the sum of the degrees of each of the vertices. So was the proof of this result clear to everyone?
Yes, ma'am.
Okay. Yeah. So this was the first basic result, and using this first result, we can also deduce that in any graph, number of vertices with odd degree will always be even. So these are two basic. Now,
I think it should be twice into edges.
oh, yes. Thank you. This is right. It should be twice. It should be twice of the edges, because each word. Each edge is contributing 2 to the degrees. So it is twice of the edges. Thank you for pointing it out. So now, uh, now and now we want to see what are trail, paths and cycle. So so first of all, what is a walk? Walk is just any alternate sequence of vertices and edges. So in this above graph, you can see. So walk is basically we are tracing out the graph in any possible manner. And it is an alternate sequence of vertices and edges. So you can see, if we start with A, F, D, again we go to A, and then again to F. So walk is just alternate sequence of vertices and edges. So in the middle you write the edge. On the left is the beginning vertex, and on the right is the end vertex. Now what is a trail? A trail, so this in walk everything is allowed, but in trail we have one restriction. Trail has to be a walk in which no edges are repeated. So the above walk is not a trail, because we can see we have this AF, we have this edge 2 which is being repeated. So above walk is not a trail. Because for trail we require that no edges should be repeated. Now path is a walk in which no vertices are repeated. So if no vertices are repeated, we'll see that no edges will be repeated too. Therefore path is always a trail. And then the other concept is of cycle. Cycle is a closed walk in which no vertex other than the first and last is repeated. So like in the above examples, all these were cycles. So you can see no other vertex other than the first vertex is repeated. Now Now, the next concept was of connected graph. So, a connected graph is a graph in which there is a walk between any two vertices. So, what we are saying by connected means if we pick any two vertices, we can reach from one vertex to another by a walk. If such thing happens for every pair of vertices, we say that our graph is connected. And components of graph are referred to as the maximal connected subgraphs of G. That is, we are looking at the maximum subset which is connected within that graph. Okay, so this was the first few lectures. Now let's solve some questions regarding these. So first question is true false. So first statement is that every disconnected graph has an isolated vertex. So what do you think? Is it true or false? So we just discussed what a connected graph is. A connected graph is that between any two pair of vertices we can find a walk, and a graph which is not connected is a disconnected graph. So first statement is saying that every disconnected graph should have an isolated vertex, and by isolated vertex we mean a vertex of degree 0. So suppose if you have this graph, this vertex is a vertex of degree 0. So this is an isolated vertex. Now the first statement is saying that every disconnected graph every disconnected graph has an isolated vertex. So
D.PL.
so what do you think? Is it true or false?
False.
Okay. So you are saying it is false. So why is it false? Like, can you give can you describe an example where can you give an example of disconnected graph which has no isolated vertex?
It is not necessary
Uh,
for it to be isolated, because you can have two component graph, which is just add one more vertex there and connect it.
Oh, very good. So what is he saying that for a disconnected graph, we just need that it should have more than one component. So in this same example, if we just add one more vertex and attach this, so this graph is disconnected, but this graph does not have any isolated vertex. So first is false. Now, what about the second one? So second is that you are given a G is a graph with n vertices and it has n plus 1 edges. So first statement is saying that there should have a vertex of degree greater than equal to 3. So what do you think? Is it true or false? So we are given a graph G. It has n vertices and n plus 1 edges. And the statement is that if such a graph should always have a vertex of degree greater than equal to 3. So think about for some time, for some seconds, and say, so what do you think? Is it true or false? Okay, so let's try looking at it. So we have a so we have this result that sum of all degrees sum of all so we have a graph G with n vertices, say v1 till vn. Yes, and we know that sum of all degrees is twice the sum of edges, and we are given that sum of all degrees is coming out to be 2n plus 2, because number of edges is n plus 1. So from the previous result we see that this is 2n plus 2. So now we have that sum of degree of all vertices is 2n plus 2. So what is the average degree? Average degree is sum of all degrees divided by number of vertices, which is just 2n plus 2, 2 plus 2 by n. So we see that average degree is strictly greater than 2. So now can you tell me, like, do you think that every graph should have every graph with n vertices and n plus 1 edges should have at least one vertex of degree 3? So first is true, because let's try, like, we have seen this average degree is greater than 2. So now I'm trying to prove that we should have at least one vertex which has degree greater than equal to 3. So this is a proof by, let's prove it by contradiction. Suppose, so we are proving it by contradiction. So suppose G has, okay, sorry, my pen start. Oh, okay. Sorry, my screen. Is my screen visible? Is my screen visible
Yes,
now?
ma'am. Yes, ma'am.
Okay, okay. So I was saying we'll prove this by contradiction. So what are we trying to prove? That if G is a graph with n vertices and n plus 1 edges, then we should have at least one vertex of degree greater than equal to 3. Suppose not, then degree of each vertex is strictly less than 3, or degree of each vertex is less than equal to 2. Now if we sum the degrees, and we see that this will be less than equal to 2n, right? Because we have n vertices and we are assuming that each degree is less than equal to 2. So this sum will come out to be less than equal to 2n. But here we know that our sum is 2n plus 2. So this is not possible. Hence we should have at least one vertex of degree greater than equal to 3. Is this clear to everyone? Why the first statement is true? Is it clear? So we were proving this by contradiction. So by contradiction, so we are assuming that this statement is not true. If we are assuming that this statement is not true, we mean that each vertex should have degree less than 3. But if each vertex has degree less than 3, and if we sum all these degrees, this sum will turn out to be less than equal to 2n. But we are already given, since the number of edges is n plus 1, the sum of all degrees is 2n plus 2. So this can't happen. And if this can't happen, our assumption was wrong. Therefore, we should have at least one vertex of degree less than 3, greater than equal to 3. So is this clear? First part?
Yes, ma'am.
Okay. Okay. So now once we have seen this, now if we have this, now the B part is the same scenario. That same B part is same scenario, that we have a graph G. It has n vertices and n plus 1 edges. And this, now we have to tell if this statement is true or not, that there should exist at least one vertex of degree greater than equal to 4. So we know that there should be, from first part we know there should be vertex of at least degree greater than 3. But this you can see is false. So because suppose if we consider this graph, so if we consider this graph, here n is equal to 4 and number of edges is 5. So this hypothesis is met, that we have n vertices and n plus 1 edges. But we can see in this graph there is no vertex of degree greater than equal to 4. Hence B part is false. So in this true and false, we see that this was false, this was false, and this was true. Now next, let's move to next question. Next question is that suppose we are given that G is a connected graph and HE is called a cut edge if G minus E becomes disconnected. By G minus E means that we have an original graph G and we are removing the edge E from that graph. So we are saying that that edge E will be a cut edge if G minus E becomes disconnected. And now we have to show that if all vertices of G has even degree, then G should have no cut edges. So first of all, we want, so what is a cut edge? A cut edge, so cut edge is that edge such that if we remove that edge from the graph, the new graph becomes disconnected. So suppose we have this graph. In this graph, we see that if we remove this edge E, then we'll have two components, one this and this. So this graph is becoming disconnected. So hence this edge E will be a cut edge. And in the second graph also, you see that if you remove any, so if I remove this edge, then this will have two components. Like we have this V1, one component is V1, V2, another component is V3, V4, V5, V6. So by removing this, so this graph is a connected graph, but by removing this edge, this graph has become disconnected. So this edge is a cut edge. So now once we know what is a cut edge, we have to show that we are given a graph G in which all the vertices have even degree. Then we have to show that G has no cut edge. So this also we'll prove by contradiction. Let G be a graph and let degree of each vertex of G be even. Then to show G has no cut edge. So we are proving it by contradiction again. So suppose G has a cut edge. So from previous definition which we have discussed just now, we know, so if G has a cut edge, what do we mean that? So we have this edge E, and we have this C one 1 component here and some another component here, and we have some vertices here and so. So E is a cut edge in this graph. E is a cut edge in this graph because if we'll remove E, we'll be having two components, C1 and C2. So now you see that all the vertex has even degree. So all the vertices in G has even degree. So tell me, so if we take this vertex, say W, which is connecting this, so V and W are the vertices which is connecting this cut edge. So since the degree of W is even, what will be the degree of W in C1? C2. Degree of W in C2. Suppose degree of W in G is 2k because we know it is even. So it is some even number. So what will be the degree of W in this subgraph C2?
2k minus 1.
2k minus 1. Okay, very good. So degree of W in C2 is 2k minus 1, which is odd. And in C2, we are given that all the vertices has even degree. So in this subgraph C2, all other vertices will have even degree, right? So can this happen? So we have in C2, W is a vertex of odd degree, and all other vertices except W, all other vertices in C2 except W has odd degree. So can this happen? So has even degree because we. So can this happen? So what do you think? Is it possible that is this possible that a subgraph of G has one vertex of odd degree and all other vertices of even degree? Is this possible?
No.
No. Why? Yes, you are right, but like. So recall. We have this result that 2 times number of edges is same as degree of vertices, sum of degree of all vertices, right? So this sum is even. So we can break this sum into two parts where we are taking odd vertices, and so first we are summing degrees of all the odd vertices. So we are breaking down this sum into two parts. First part is corresponding to odd vertices and second part is corresponding to even vertices. So this part is even because it is a multiple of 2. So we know that this part is even because it is a multiple of 2. And here also all the vertices are even vertices, so we are adding up even numbers. So if we add up even number, this sum will also turn out to be even. So what will be this sum? This sum also have to be even, because when we add an odd number and an even number, we can't get an even number, and on the left hand side we have an even number, so this sum also has to be even. And we are adding and this but we are adding odd numbers, so this should so the number of odd vertices should be, this sum can be even only if we are adding even number of vertices. So number of vertices with odd degree in a graph should be even. Is this clear? So we have shown that in any graph, number of vertices with odd degree should be even. But now in our case, we are getting a subgraph C2 which has one odd vertex but all other vertices with even degree. So we are getting odd number of odd vertices. This can't happen. Therefore, we have arrived at contradiction, and G cannot have a cut edge. So is this proof clear? I can repeat any of the step that is not clear. If it is not clear, you can ask.
Ma'am, how is it 2k minus 1, ma'am? I am not getting in.
Okay,
C2.
okay. Yes. So see, degree of vertex W was 2k. So now what is the degree of now we are saying that degree of vertex W in C2. So in C2 there degree of vertex is 2k. So one of the degree is contributed by this edge E, but this edge E is not present in this subgraph C2. So therefore it will be degree of W in C2 will be 1 less than its original degree. So originally it was 2k, so now it will be 2k minus 1. Is this clear? In C2 we are not so in the complete graph
Okay, ma'am.
G,
Thank you.
it okay,
Yes.
yes. So now we see, so in this graph we are getting a vertex with, so if we consider just the subgraph C2, we are getting one odd vertex and all the rest of the vertices are even. But this can't happen because we know in a graph G all number of vertices with odd degree should be even. So is this question clear to everyone? Can we go on to next question?
Yes, ma'am.
Okay. So this is the question, this is one of the question I picked from quiz 0, so you might be aware of this first question. So first question is that there are 15 telephones in town, can we connect them so that each telephone is connected with 5 other telephones? So what do you think? So we have 15 telephones. So if we first of all, let's model this problem into a graph theory problem. So we have 15 telephones. So we are saying, so our graph, so all these telephones are corresponding to 15 vertices of the graph. And if suppose, so we are calling them telephone T1 till T15, and we are saying that T1, Ti and Tj are connected if Ti Tj Ti Tj, if Ti Tj are connected, then Ti Tj is an edge in G. So now our question becomes that, can we have a graph G? Now the graph theory problems become that, can we have a graph G with 15 vertices and each vertex has degree 5? So is this possible? A graph with 15 vertices such that degree of each vertex is 5. Can we have such graph?
No.
Okay. Why do you think no?
The sum would be 75, which is an odd number.
Yes, good. So sum of all degrees will be 15 into 5, 75, which is odd. And we know that sum should be even. So this can't happen. Or other way to say, like we used in the previous problem, number of odd vertices in graph G should be even. And we see all the vertex, since all the vertex at degree 5, all the vertices here have odd degree. So we have 15 odd vertices. That is not possible. So we see the answer to A is no. We cannot have 15 telephones in a manner that that each is connected with 5 other telephones. So for the first we get that it is no. Now the second problem is this: can we have a simple graph with following degree sequence? So what is a degree sequence first of all? Degree sequence is basically you are listing down the vertex degree of each vertex in a ascending order. So you see here we have 1 2 3 4 5 6 7 8. So we have basically, we are saying that we have 8 vertices and degree of first vertex is 1, degree of second vertex is 2, degree of third vertex is degree of, so these are giving the various degrees of each vertex. So dv1, dv2, dv3 and so on. So can you so do you think we can have a graph with following degree sequence? So first of all, whenever some degree sequence is given, first thing to check is that if the sum is even, because we know that sum of all degrees should be even. So in this case we see the sum is coming out to be, if sum is even, or which is equivalent to saying that number of odd vertices, count number of odd vertices, number of odd vertices should be even. So in this case we see that this is an odd vertex, this is an odd vertex, this is an odd vertex, this is an odd vertex. So we have even number of odd vertices, so sum will turn out to be even. So first condition is met. So we don't so first condition is met, so we can't conclude anything from this, that if we can have a graph with following degree sequence or not. But can you think of any other reason why a graph with following degree sequence cannot happen? We know that we are given 8 vertices and we are because these are 8 numbers, we have 8 vertices and we are also looking for a simple graph. So our question is that this: can we have a simple graph with following degree sequence?
No.
Okay, so somebody said no. Why do you think it's no?
The number of vertices cannot be equal to number of edges.
Okay, number of number of vertices cannot be equal to number of edges.
Yes.
Oh,
Ma'am, we have 8 vertices. For that, we need one more. Like vertices should be greater than 8. So it should be like 9 or 10. Then it is possible. Yes.
oh, okay. Uh, but number of vertices can be equal to number of edges. See, if you have, so these are 3 vertices and 3 edges. This is giving you a graph. But here also, so here, and in this case, number of edges is not equal to number of vertices, because this is, so this is a degree sequence. So you are, so we have, so if we calculate this sum, it will come out to be 8, okay, 7, 14, 20, 24, 26, 27, 28, and 8, 36. So we see this. So number of edges is 18 and number of vertices is 8. So in this case, number of edges are coming out to be 18 and number of vertices coming out to be 8. So that reason can't happen here, and also that is not true, because see, in this graph, in this we have this, in this, so we can have that number of vertices in a graph is equal to number of edges. If we consider this graph has 3 vertices, 3 edges, so that thing is also possible. But okay, let me tell you that this is, we cannot have a graph, we cannot have a graph of this type. Now can you think, like, why cannot we have a graph? Is there anything else which is very evident that this cannot be a graph?
DV1 and DV2 have same one vertices.
dv1 and dv2 have same degree, you're saying?
Yes.
Okay, but that is, that won't,
8,
yeah, yes, but that
8
won't
vertices will give 8C2 number of edges. So
okay, but like 2 vertices can have degree 1 also. See, if you see this graph, this is a graph, and both the vertex have degree 1, so that this is also not a problem.
Ma'am, there are two vertices with degree 7,
Okay, yes,
and there are total number of 8 vertices. Means these two vertices are there are parallel edges between these two vertices.
okay, so you are saying if we have, if we have 2 vertices of 7 degree, uh, so yeah, so if we have v1, v2, v8, if two vert, so you are saying that since they have two, there will be a parallel edge.
Yeah.
uh, no, that is not, that need not be true, right? So if you have, see, v1 and v2, so you are basically v1, oh, okay. Hmm.
Because there were degrees n minus 1.
But like, see, so we can have, wait, like, that should not be a problem either. uh, or let's see if it is a problem. So 1 2 3 4 5 6 7 8. So if I'm like, basically, if it is degree 7, that means it is connected with each of the vertex, right? It is
Yeah.
connected. So see, I'm connecting this each with each of the vertex. Now I can connect this vertex with each of the vertex also, then so that won't be a problem. Two vertices can have degree 7, because in, see, if you take C7 complete graph with 7 edges, all the vertices have 7 degrees, so this can also happen.
Ma'am, there
Correct,
is
Satyam Sriram.
It has 8 vertices, right?
Yes,
Um,
yes,
Last one has degree 8.
yes,
It can't share like 8 degrees. Na? Total number of vertices is 8.
yes, this is right. So yeah, because total number of vertices is 8, each vertex can have degree at most 7, so we cannot have a vertex with degree 8, so this is the problem. That's why we cannot uh, so we cannot have a vertex of degree 8. Hence we like in a simple graph at least. We are assuming this graph is simple.
Apply Hakim's theorem.
Yeah. Sorry.
You can apply Hakim's theorem.
Okay, but we don't need we don't need to apply any theorem. Like it is like without the theorem also we are getting that, because we have 8 vertices. Any vertex can have degree at most 7, because if we have 8 vertices, this first vertex has only 7 options.
But it takes time, no? That's
Yes,
it.
no, no. Like if you apply the theorem, it will be solved in the first step itself. So the
Yeah,
Okay.
that's
like
why.
no issues.
Okay.
Otherwise, it will take time to guess.
Yeah. Okay. Yeah. Yeah. But this was like this was for like so if we have 8 vertices, we cannot have a degree 8 vertex. This was also fine. Okay. So now is this clear to everyone? We move on to next question?
Yes, ma'am.
Yeah. So next question is that we have to find Eulerian train in the graph below using Fleury's algorithm. So first of all, okay. So first of all, what is an Eulerian trail? So what is an Eulerian trail? It is a closed trail which contains all the edges. It is a closed trail which contains all the edges. So do we have so we also have this result that a graph is Eulerian, and if a graph has a Eulerian trail, that graph is called Eulerian, and we say that a graph is Eulerian if and only if each vertex has even degree. So in the class, in the lectures, we saw the proof of this theorem. If each vertex has even degree. So to show the one way round of this theorem, that if each vertex has given degree, graph is Eulerian, the proof uses this Fleury's algorithm. That is, we have to to find an Eulerian trail. So first of all, if a graph has Eulerian trail, all the vertices should have even degree. So in both these graphs, you can see all the vertices have even degree. So Eulerian trail do exist. Now now we have to find the Eulerian trail. So anybody has any suggestion how to go about it? So this is my graph 1. So first I'll recall the procedure, recall the algorithm for finding Eulerian trail. So first it is that we start with some vertex V, and then go to an edge whose deletion is not increasing the number of connected components. So this is the first step. That is, we pick up any vertex, then we choose that edge whose deletion won't increase the number of connected components. And if no such edge occur, if no such edge is there, then we can go to then we can choose any edge, and we keep removing the edges in our trail, and repeat this procedure to get the Eulerian trail. We keep removing the edges in our trail and repeat. So this is an algorithm to find the Eulerian trail. So in this first graph, so what is our algorithm saying? We pick a vertex A. So suppose I have picked vertex A. Now among the possible choices, I have to choose that edge whose removal won't increase the number of components. So I have two options, AE and AB. And if I remove AB or AE, suppose if I remove AB, number of connected components is not increasing because I can still connect AB through AE. So we can do this. So first step is I am going from A to B. Now now the algorithm say, now choose, now we have removed this edge AB. Now the next edge we have to choose in such a manner we have to choose a edge B in such a manner that its deletion won't increase the number of connected component. So first of all, we have three options: BC. Either we can choose the edge BC, we can choose the edge BD, or we can choose the edge BE. So first of all, can we pick edge BE according to the algorithm? So we have to pick an edge whose deletion won't increase the number of connected component. So suppose I remove BE and I have already removed AB. So what is the number of connected components now after removal of BE? Uh,
2.
2. So we can't. So yes, good. So we can't choose BE. That means, right? According to our algorithm, we can't choose BE.
BC can be chosen.
Yes, but we can choose BC because if we remove BC, the number of connected components remain same. So next we'll choose BC. Now we just have one option, so we'll have to choose this only. Again we just have one option. Now we just have one option, so we can just we'll get our Eulerian trail. So we have ABC. Our Eulerian trail is ABCDBEA. So we get an Eulerian trail for the first part. Now let's see for the second graph. So in second graph also, let's start with A. So can we choose any of these edges? We have two options, AB and AF. Can we choose any of these edges? Yes.
Yes, we can.
Yes, because if suppose I am choosing AB, number of connected components remains same. So I can choose AB. Now I have three options: BF, BD, BC. And here also you'll see, yeah, here also we can choose anything and it won't increase the number of connected component. So let's choose BF, because if I'm wait, we can't choose BF because, yes, we can't choose BF because, okay, so from B we have three options, BC, BD and BF. If we choose BF, What is the number of connected components? Number of
One
connected,
only.
one only. So we can choose it. Yeah. Okay. Now, now we have three more options. Now, when we reach F, we have three options: F E, F D, F A. Now, can we choose F A? No, because if we choose F,
So,
we can't choose FA because then we'll have an isolated vertex and number of connected components will increase. So we'll choose either D or E. So let's choose D. So we have A, B, F, D. Now we have three options: D, B, D, C, D, E. What options can we choose? So if we do DB, then we have no issue. What was you suggesting? So if we choose DB, we have no issues. If we choose DC, then also we have no issues. If we choose DE, will we have issues? Yes.
No.
Yes, we'll have issues. If we choose DE, then we'll have two components: AFE and BCD. Suppose if we choose DE, then we'll end up with two components. So we can't choose DE. We have to choose anything between DB and DC. So let's choose DB. And now we just have one options. So we see that we now at every step we'll have just one option. So we'll get our Eulerian trail. So B, C, D, E, F, A. Okay. So is the algorithm clear to everyone? So give if we have to find an Eulerian trail, is the following algorithm clear to everyone?
Yes, ma'am.
Okay. 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 So I am hearing some noise. Yeah. Can you please unmute if you have no question? There is some noise. Yeah. So, Pushpa, can you please mute yourself? Thank you. Uh, okay. So now next problem. So now the next question is, it is a question from from your practice sheet, that can there be a simple Eulerian graph with 6 vertices and 7 edges? So have you guys tried this question?
Yes. Yes, ma'am.
Okay. So what do you think? Can there be a graph with such things?
Yes. 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 It is possible.
Okay.
It is there.
Okay, so can you okay, how did you find that graph? Uh, can you describe your graph if it is possible to describe? Yeah. So, okay. So it's possible you're saying. Okay,
Yes.
okay. So we have 6 vertices. Let's try to construct the graph. So if it is possible, we should be able to construct a graph. 6 vertices and 7 edges. So I have 6 vertices: V2, V3, V4, V5, V6. And I have 7 edges. So what is the sum of degree? Sum of all the degree of vertices is twice the number of edges, which is 14. Now, we know that a simple Eulerian graph, now the simple Eulerian graph should have all the vertices of even degree. So my first question is, what are the possible degree sequences? Possible degree sequence for such graph. Possible degree sequence for such eulerian graph. So we have six vertices. We have six vertices, and the sum of degrees is 14 because we have 7 edges. So what is the possible degree sequence for a simple eulerian graph? And all the vertices should have even degree also because this graph is eulerian. So what is the possible degree sequence?
4, 2, 2, 2, 2.
Yes, good. Because see, yeah, so the only possible degree sequence is this 4, 2, 2, 2,
2, 2, 2.
2. Because first of all, an Eulerian graph is a connected graph. So we cannot have an isolated vertex. So each vertex degree should be greater than equal to 2. And if each vertex is degree is greater than equal to 2, and if we are giving 2 to each, we already get 12, and we are left with 2 degree. But all the vertices can have even degree, so this 2 should go to one vertex. So we see that this is the only possible degree sequence. Is this clear why this is the only possible degree sequence for Eulerian graph with 6 vertices and 7 edges?
Can you once more repeat, ma'am?
Yes. Yes. So since first of all, since this graph is Eulerian, it is a connected graph. G is connected, and since G is connected, G cannot have a vertex of degree 0. Do you agree till now that G can't have a vertex of degree 0?
Yes.
Now G cannot have a vertex of degree 0, but this is a simple Eulerian graph. So that means degree of each vertex should be at least 2, because it cannot be 0, it cannot be 1. So at least it should be 2 or some other even number. So now if I give degree 2 to each of the vertex, so if I sum it up, it will come out to be 12. But total sum degree is 14. So I have to assign degree plus 2 to some vertex. But I cannot assign plus 1 to 2 vertices. So there is only 2 possibility to do that. Either I assign plus 1 to 2 vertices, or I assign plus 2 to 1 vertex. But I cannot assign plus 1 to 2 vertices because then we'll have 2 vertices of odd degree. But a simple Eulerian graph cannot have a vertex of odd degree. Therefore, we have to assign plus 2 to one vertex, and therefore this is the only possible sequence. Now is it clear? Now is it clear?
Yes, ma'am.
So now once you see that this is the only possibility, now you just have to construct a graph. So it has degree 2. So okay, so let's do this. Okay, sorry. So we have to do something with we have to construct a graph with following degree sequence. So I know that one vertex has degree 4. So V2, V3, and there is one more vertex, V4. So we see that V1 has degree 4. So V1 cannot have so this is 3, sorry, and V5. So V1 has degree 4, and these are the sequence. But rest all the vertices have degree 1. Rest all the vertices have degree 2. So if I do this, we see that V4 has degree 2, V2 has degree 2. So if we do this, no, wait, no, something goes wrong. Uh, oh. So I have 1, 2, 3, 4. So this has what? V1 has 1, 2, 3, 4, 5. Now V5 already has, so we can join it this 1. Now this has degree, now this has degree, V1 has already has degree 4. Now V5 has degree 2 and V4 also has degree 2. So if we do this, now also we see that this also has degree 2, this also has degree 2. Uh,
Ma'am, this one is having what, 5 edges. Sorry, 5 vertices.
yes, yeah. Okay. Okay, we need one more edge. Yeah. So, okay. So this won't work. Uh,
Yeah, by making some small change in that previous graph, you can construct, I guess. Like
okay.
the same graph.
Yes. Yeah, can. So what should we do? Yeah.
You just construct the previous graph. I will let you.
Okay. So see this. Yeah.
Yeah, now just like just put the numbers. Yeah.
V5. Yeah.
Remove the edge between V4 and V3.
Okay. And yes. Okay. Me make a square.
Yeah,
Yeah. 3.
it's possible.
Yeah. Yes. So we see that we are getting a. So we see that we are getting a simple Eulerian graph with we are getting a simple Eulerian graph with 6 vertices and 7 edges. Okay. So now next problem. So this is also one. This is also a problem from your practice sheet. So this this says that let Cg minus S denote number of components of G minus S. So we have a graph G. S is a subset of vertices. S is a subset of vertices, and G minus S refers to the graph when we remove when we remove the vertices in S. And let G be Hamiltonian, then we have to show that for every proper subset S of V, the number of components of G minus S should be less than equal to number of vertices in S. S is a subset of V. So have you tried this question? Oh, okay. So has anybody tried this question?
Yes, ma'am. I
Oh,
took one example
okay. Yeah.
of of
Let.
uh, of, of
Hmm.
connected graph,
Okay.
and I remove one vertex from it.
Okay.
Then it becomes a two component
Okay.
of G,
Okay.
and
But
I showed that components is less than or equal to that subset of vertex.
okay. So you mean that you saw it with some example that this is true.
Yeah.
Okay. Yeah. Yeah. That is that is fine. But yeah. Okay. Bu- But do you have any idea like how can we like it is working with some example, that's fine. But how can we prove this?
Mm,
Hmm. So first of all, okay, what is so we are given that G is Hamiltonian. So what is a Hamiltonian graph? Hamiltonian graph is graph having a Hamiltonian cycle. And Hamiltonian cycle was basically a a cycle containing all the vertices of G. Now the question is saying that if we are given a Hamiltonian graph, then if we remove some vertices from it, so suppose if we are removing k vertices, then number of connected components of the resultant graph after removal cannot be more than k. It has to be less than equal to k. So let's try it with, like, let's try it for some set. So we are suppose G is Hamiltonian. Suppose G is Hamiltonian. So that means we have an Hamiltonian cycle. Say this G has n vertices. This G has n vertices. We'll be having some cycle. Is there any question? Hepzibah, is there any question? So we are given that G is a Hamiltonian graph. So that means we have a Hamiltonian cycle. And if that means we have some cycle between the vertices which is covering all. Sorry. So if G is a Hamiltonian graph, we have some cycle. Suppose this. Now suppose, so the question is saying that suppose we remove k vertices, then the number of and we can have, so so if graph is Hamiltonian, we'll have a Hamiltonian cycle, and there can be additional edges also, but we know that there will be a cycle which is covering all the vertices because G is Hamiltonian. Now the question is saying that if we are removing some k vertices, then after removal the number of components should be less than equal to k. So suppose first we do it for k equal to 1. So we have to show that in this graph, that if we removing one vertex from Hamiltonian graph, after removing one vertex from Hamiltonian graph G, G remains connected. Right? So we are trying to prove this for special case when your S is just one vertex. First we are trying to prove this theorem for one vertex. So what does this theorem turn out to be for one vertex? That the number of connected components should be less than equal to 1. That means number of connected components is 1.
This part, ma'am, once more.
Yeah. Okay. Wait. Number of connected components is greater than equal to S. Or wait, no. Less than equal to 1.
Less than or equal to
1. Yeah, sorry. So we are first doing it. So we are first doing it for k first. So this is a question for S is some subset of vertices. So first we are trying to prove this theorem when S has just one vertex. Suppose S is Vk. So now this question become that number of connected. So if we remove one vertex, number of connected components should be less than equal to 1. So that means number of connected components should be 1. Number of connected components can't be 0. So number of connected we have to basically now show that after removing one vertex from Hamiltonian graph G remains connected. So can you see if this is true or not? So we are given a Hamiltonian cycle. We have a Hamiltonian graph. That means this Hamiltonian graph has a Hamiltonian cycle. That means a cycle which is covering all the vertices. Now we are saying that if we remove just any of these one vertex, this graph should remain connected. Is this true? Suppose I remove V2. Suppose I remove V2. Will this graph remain connected?
No, ma'am.
Okay, why? We also have a edge here because see, so this is a Hamiltonian cycle. So if this what I have drawn is an Hamiltonian cycle. So basically I'm starting with, it is a cycle which is starting with V1 and ending with V1. And now I'm saying from this Hamiltonian cycle I'm removing one vertex V2. So is this graph connected after removing this vertex V2? Will this graph remain connected or not?
No.
Okay.
Yes.
Okay. So first of all, somebody is saying no. So why no? Why no? Why this graph won't be connected according to you?
Because if you remove two vertices from the cycle, Hamiltonian cycle, then the component, there will be two components.
No. For the first part, I'm just saying that I'm removing just one vertex. If I'm removing just one vertex, will the graph remain connected or not?
Yes, it will be connected.
Okay. So why
If
will
you
it be
remove one vertex, it will be connected. But
Yes.
if you remove two vertices,
Yes.
then it will not be connected.
Then it might or might not be connected. Yeah.
Yeah.
Yeah, but for the but in this question, for the first case, I'm just saying that we have just one single vertex. So this question is reduced to showing for this particular case when S has just one vertex, that after removing
Yeah.
one vertex, this remain connected.
Connected. Yes.
So
Yes.
for k equal to 1, this is true, because if we remove v2, so we see that only all the other pairs are connected, but so we by removing v2, connectedness of graph is not affected, because to reach to reach v1 and v3 we can go from this other path, from this other arc, and rest of the graph is remain connectedness of rest of the other pairs is unchanged. Right? So if I am removing v2 and if I am removing v2, I am left with these vertices till v1, v and v3, and all of them are connected by a path. So we see that graph remains connected. So for s equal to 1, this is true. For when we are
Yes.
removing one vertex, this theorem remains true. Now let's
Yes.
look at when s has two vertices, when we are removing two vertices. That is when S has two vertices, say V1 and some V1, Vi, Vj. So now we have to show number of connected components. Number of connected components are less than equal to 2. That is, we cannot have 3. So we have to show that after removing two vertices from Hamiltonian graph, we can have either two connected components or one connected components.
Yes.
So can you think why that is true? So see, again if we have this, So we are removing any two random vertices. Suppose first I am removing V2 and Vn. So how many connected components do this graph have now? After removing V2 and Vn, so basically G minus V2 and Vn. How many connected components this graph has now?
2.
2. So, okay. So this is, and this is K, and if I remove V2 and V3, instead of V2 and Vn, if I remove V2 and V3, then
It is
how,
again 2.
then there we have just one connected component, right? If I'm
Uh,
removing V2 and V3, then all the other then all other are correct. So we see if we are removing two vertices, we are either having one component or two component. So this is true for removing two vertices also.
yes.
So now using these tricks, now you try yourself using this trick, using this these tricks, try to do it for general S. That if you are removing k vertices, the number of connected component cannot exceed by k. Okay, but is the case for one vertex and two vertex clear to everyone?
Yes.
Is it clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, now the next question is this: you are given this following graph and you have to tell if this graph is Hamiltonian. So now you, now,
Ma'am, previous question, how we will conclude? Like we have done for k is equals to cardinality of s equals to 1 and then 2.
cut 2,
Then,
yes. Yes, so I'm saying I'm leaving that general case to yours, to you. Like
okay,
using these same tricks, try to prove it for general case.
okay,
It is it.
like, okay, s is having suppose k elements like
Yes,
that.
yes, yes, yes. We had like I have shown it for one vertices and two vertices. Now try to prove it for general case, that if you are removing k vertices, can the number, like, then the connected number of connected component cannot exceed k. Okay. So like you try it like this time. Like if you couldn't like get the answer, we can discuss it in the next tutorial session.
Okay,
But but it is a similar technique, so I want you all to try it yourself first.
okay.
Now, so from previous question, we know that in a Hamiltonian graph, if we remove k vertices, number of connected components should not exceed k. So using that result, can you show that this graph is not Hamiltonian? So I'm giving you a hint that this graph I'm telling you is not Hamiltonian, and it will be using the previous question. Now now can you say why this graph is not Hamiltonian using the previous question? There are other hints also spread over the sheet. So this graph is not Hamiltonian. Hint, use previous question. What was previous question? That if we are removing k vertices, this new graph has less than equal to k connected components. So this is your hint.
Ma'am, if we remove
the vertex G, A, and C.
Okay, if you are
Then we get more than three components.
okay, if you are removing A, G, and C.
Yes, ma'am.
Okay, let's see. If we are getting more than three components. Okay. So what are your three components then? If you are removing A, G, C, so give me the more than three components. Give the more than three components. Like
E, F, J, and I. We get four isolated vertex E, F, J, and I.
okay, you are saying if we are removing A, G, and C, we are getting
E, F, J, and I isolated vertices.
no. They are not isolate. E is also connected via K, right? So E is not isolated. E is also connected through K. And E is connected to K and it is also connected to J. So E and
Yeah,
J
yeah,
becomes
yeah.
connected.
Yes, yes, ma'am. Yes. Hmm.
Those vertices given in the right A, C, K, E, G, if we remove those, then 6 components we are getting.
Okay. So yeah. So if we remove A, so see if you see that if we remove this, this, and this, like if we are removing these five vertices A, C, K, H, G, then we see that all the rest of the after removing these five vertices, all other vertices become isolated, and we are left with six vertices. So we are left with six components, but we are removing five vertices. Therefore, this graph cannot be Hamiltonian. So is this fine?
Yes, ma'am.
Yeah. Okay. So this was like what?
Ma'am,
Yeah.
for a graph to be Hamiltonian, we need to come to the starting point. After going through all the vertices, we need to come to the starting point.
Yes. Yes.
Okay.
Because graph to be Hamiltonian, we mean that we need a Hamiltonian cycle,
Hamiltonian.
and cycle always start and ends at the same point. Yes. So these were the questions for today, but now now we can discuss any of the doubts you have. So you're free to ask any question related to today's session, or from lectures if any doubts you have.
Ma'am, can you just go through from first question to the seventh question? I joined late. I'll just take the screenshots.
Okay, yeah. Okay, but I will also upload the video plus the notes also.
Oh, so it will be uploaded?
Yes, yes.
Okay, okay.
Then do I need to go to the
No,
slide?
no, no,
Okay.
no. Okay.
Okay. Yeah. So any questions? So were all the questions today clear to you?
Yes, ma'am.
Okay. So any questions
Hello.
from yeah, yeah, yeah.
Hello.
Hello. Yes. Yeah.
In practice assignment,
Hmm.
there are many questions on probability, and we have to solve this question using graph theory.
Uh, so in the week zero assignment, there were like few questions related to probability.
Yeah.
No. You don't need to solve them from using graph theory. If you can solve them directly, then it's fine.
Okay.
So that was just week zero assignment. Like
No,
in
because in the assignment one also there is one question on the probability.
which question you're saying? Can you like?
In assignment one,
Hmm.
question number 8, there is one question on probability.
Okay, wait. Let me check. Wait.
Uh,
Uh, in the graded assignment, you are saying?
yeah, yeah.
Uh,
Last question. You have to say it is true or false.
Okay. Uh, mhm. So if you are using but like I think this question you need to do it like if it will be preferable to do it by graph theory.
Okay.
Yes. This is a graph theory problem. So I was referring to that coin tossing. Like there in week 0, there were some problems on coin tossing and all. That was
Yeah.
I thought that you were considering those, but I think no. Like from these like from the graded assignments, you have to do graph theory.
Okay.
That
But
question
if
can
you,
that eighth one.
Yes. Yeah.
yeah, yeah, how to solve the probability question using graph theory?
Oh, okay. It is not. It is not a problem. Uh, okay. Okay, it's for so this is like you have to give a true and false thing. There are
Yeah, yeah.
every member. There are 99 members in a club, and every member. So see,
How?
like in this so I won't be telling the solution, but there are so you have to basically this in you have to first turn this into a graph theory problem. So there are 99 members in a club. That means you have 99 vertices.
Okay.
And every member claims that he will play bridge with only with someone he knows, and each member know at least other 67 members. So
Yeah.
you can say so since each member know at least other 67 members, so this is in a way giving you a degree for each vertex.
Mm-hmm.
Because so in this case, if you want to convert it into a graph theory problem, your vertices are members, and if two members know each other, then there is a edge connecting between those members.
Okay.
And now you show that there must be a four members who can play bridge together. So basically you have a subgraph of four vertices which is connected with each other vertex in that four thing, in those four vertices. So you have to show that.
Mm-hmm.
Up to the degree 67. That, but after that, can you say that?
Yeah. So each vertex will have degree 7. Then the question is saying that okay. Then question is saying that there must be four members who can play bridge together. So that means you have to show that there are four vertices. So basically there is a subgraph of complete. There is a subgraph of four vertices which is complete. So you have a so by that I mean like this. Uh, so basically you have some graph with 99 edges,
Mm.
and degree of each vertex is greater than equal to whatever the number was, 65 I think.
67.
67, yeah. So degree of each vertex is 67. Then they are saying that there are at least four vertices, so which are such that in that everyone knows each other. So that means you have to say that there exists a subgraph of this type in this graph. So you have a graph with 99 edges, and and degree of each vertex is greater than equal to 67. Then you have to say whether that graph always necessarily have such subgraph or not. So this is the question.
Mm-hmm.
Is this fine? The question? Okay. So in
Okay.
yeah. So any other questions?
Yeah, yes.
Yeah.
And next class will be next Sunday.
Yes.
Next.
Next class will be on next Sunday, same time. So if you have no further questions, you can leave the meeting. Or if you have any suggestions or like suggestion questions, anything you can say.
And exam will be on MCQ basis.
Uh, okay, that
Exam.
I am not like I'm not entirely sure. That I think you can ask in the forum. I am not sure about that.
Okay.
Ma'am, your Hamiltonian cycle,
Hmm.
can two vertices be repeated, or only one has to be repeated? I mean, the starting one should be
No,
repeated.
no, only one, only the first. So in the Hamiltonian cycle, in the in any cycle, only first. So we are not, you are not allowed to have any repetition. It is just that it should start from V1 and end with V1. But in middle there should be no repetitions. So
Yes, ma'am.
same for the Hamiltonian cycle. So so Hamiltonian cycle is a cycle which has all the, but it should have, but that cycle should have all the vertices of the graph.
Okay.
Madam,
Yeah.
madam, what's the difference between necessary condition and sufficient condition? Because the
Okay.
last question you saw, the
Yes.
component of G minus S is less than or equal to
Yes.
S.
Yes. Yes.
Is that a necessary condition or sufficient?
Yeah. So that is a necessary conditions.
Okay.
So see. So G is Hamiltonian. G is Hamiltonian implies that thing that, so by necessary condition we mean that every Hamiltonian graph should have that condition.
Yeah, it is
if
necessary.
if something is a necessary condition, suppose P is a necessary condition, that means every Hamiltonian graph should have that property P. But for sufficient but sufficient for sufficient condition is that, if necessary condition is this, that every Hamiltonian graph should have that P. But if some Q is a sufficient condition, if Q is a sufficient condition for Hamiltonian graphs, by this we mean that, if Q is a sufficient condition for Hamiltonian graph, by this we mean that if a graph G has Q, then G is Hamiltonian. So by sufficient a sufficient condition need not be true for all Hamiltonian graphs, but if a graph has that condition, then we say that G is Hamiltonian. So hence we say such condition is called a sufficient condition. And necessary condition is that if P is a necessary condition, that means that every G, every Hamiltonian graph must have P. So in our question, it was seventh. Oh. So in our question we have this, that uh, if G is Hamiltonian, we show that every proper subset S of V, for every, like after removing any proper subset of vertices, the number of components cannot exceed the number of vertices which are removed. So this is a necessary condition because it is true for all Hamiltonian graphs. But the condition that you did, in the lectures, that was a sufficient condition.
That is Dirac's theorem, no?
Yes, yes, the Dirac's theorem was a sufficient
It,
it gives you a
that is okay.
sufficient condition. Any other question?
And what about Or's theorem?
Sorry.
Or's theorem. Or's theorem is also there, no?
Okay. Which theorem? Can you state the theorem? Like,
Something like that. Or's theorem.
okay. Sorry, I don't know which theorem you're saying. What? Oh. Halls. Halls. You mean? Hall.
Yeah, yeah.
Okay. What was what was I don't remember the statement. Do you remember the statement? This was not like Hall's theorem was not done in the first week, right?
Yeah, yeah.
Okay, so like so you want to know if it is a necessary condition or a sufficient condition.
Yes, yes.
Wait, like Hall's uh, so okay. So like you so if you so I see that Hall's theorem this is for the matching problems, right?
Hmm.
So maybe like maybe we can discuss it when it comes then. Is it fine? Like maybe
And can you explain old assignment question two?
which question?
Like question is, ma'am, like an independent set is a set of vertices in a graph, no two of which are adjacent. Every graph with diameter 10 has an independent set width.
Okay.
It's in old assignment, ma'am. Assignment 2, question 4.
Okay. Assignment 2, question 4. Let me check. Wait, I'm opening it. Assignment 2, question 4. The grade you are asking about the graded one? Graded the assignment graded assignment.
Yes, ma'am. Like
Graded one.
But
old assignment, ma'am.
Yes, it is true.
okay, so in the assignment I have is the graph below bipartite. I don't have like what you are saying the question.
I think it's non-graded, ma'am.
Oh, okay, okay, non-graded. Question number 2. An independent set is a set. Okay, I got this question. So wait, let me present the screen. Yeah. So an independent set is a set of vertices in graph, no two of which are adjacent. Every graph with diameter 10 has an independent set. Okay, so you want to know what is the meaning of independent set? So you see, so this is basically saying an independent set is a set of vertices, no two of which are adjacent. So basically, you are considering a subset of by independent set you mean a subset of vertices in which like if so suppose you are taking the subset v1 v2 vk, then no two of those vertices will be connected by an edge. So that is an independent set. And now the question is, so if you have a graph with diameter 10, then you have to say which of these things is true, that it should have an independent set with at least 6 vertices, or so basically you have to tell if we can have a subset of vertices v1 till v6 such that no two vertices are adjacent to each other. So you have to say tell which of these three, which among which of these three which will be true always. So like this is the question, but like we'll be discussing week 2 assignment in the week 2 thing. So if you want to understand the question, this was the question, but like I can't discuss the solution today.
Okay, ma'am.
So if you have any questions from week 1, you can ask. Okay, so if there are no further question, uh, uh, I'll stop the meeting. Okay, thank you.
Thank you, ma'am.
Thank you, ma'am.